If you're just tuning in now, you have missed videos 1 through 3 and all the excitement around electricity, DC circuits, magnetism. Go back and hit that up. That is some primo stuff. What we're going to talk about right now, though, are waves. Before we can talk about the interesting things that waves do, we got to know the general terms. So amplitude would be the length, or let's say the vertical distance. If we're talking about a wave that's propagating and moving horizontally, the amplitude would be how high above the midpoint the crest is, or how low below the midpoint a trough is. If you're measuring from the height of a crest to the height of a trough, technically that's 2 times the amplitude, so be aware of that. Now a wavelength is the distance from a crest to a crest, or a trough to a trough. As it is just simply a distance, it'll be measured in meters, or some metric prefix followed by meters, like nanometers. Be aware that a midpoint to a midpoint is technically only half a wavelength. The definition of a wavelength really is once the wave begins to repeat its motion again, you have traveled 1 wavelength. So if I go from midway between a crest and a trough, I go over a crest, down under a trough, and then back to a midpoint. That is 1 wavelength. Another way to remember it is from the midpoint up to a crest is always 1/4 of a wavelength. And a wavelength is denoted by the Greek letter lambda. We talked a bit about the difference between transverse and longitudinal waves. Transverse consists of crests and troughs and the particles, the medium making up the actual wave, move at 90 degrees to the wave itself, or to the pulses of the wave. Longitudinal waves consist of compressions. This is where the particles are tightly packed together, and rarefactions, where they're spread apart, rather than crests and troughs. The motion of these particles is in the same plane as the direction of the pulse itself. So kind of like a sound wave. This is caused by variations in pressure at different regions in space. So sound waves need some sort of medium to travel through because that's how you're going to get pressure. A few more wave terms. The period is the amount of time it takes for a wave to travel 1 wavelength, be it a longitudinal or a transverse wave. The frequency is the number of wavelengths that pass by any given point in 1 second. So the period is how many seconds per wavelength that's being traveled, and a frequency is how many wavelengths per second is coming by. So they're total inverses of each other. A wave speed is just how fast the wave pulse is moving. This is in meters per second. And again, a wavelength is the distance until the wave repeats its motion. So compression to compression, rarefaction to rarefaction, crest to crest, trough to trough, all wavelengths measured in meters, or some flavor thereof. In general, the wave equations you're going to need to know is that the frequency is 1 over the period. All right, that's not too bad. And here's the big one. The velocity of the wave equals the wavelength times the frequency. You can use this for literally any wave. You'll need to know as well about superposition. Superposition is just 2 wave pulses combining when they meet each other. You can get 2 different types. Constructive interference, that's where a crest meets a crest. Or if the trough meets the trough, amplitudes add together, you get megatrough. Then you've got destructive interference. This is where a crest will meet a trough. The amplitudes will actually decrease, or in some cases they'll cancel entirely. Either way, if you look at the amplitude vectors, they'll just add together. One quick note on this is after they interfere, be it constructive or destructive, the 2 wave pulses just continue to travel in the direction they were traveling as if they had never met that other pulse. It's kind of weird. So if A is a crest and B is a crest, they're heading toward each other, they meet, mega crest, and then they continue onward. A and B, basically untouched. It's even weirder when you think of destructive interference. If, let's say, A and B have the same amplitude, but they're on opposite sides, they meet, destructive interference, but then they continue to pass through each other, and A continues on its merry way and B continues on its merry way, both apparently blissfully unaware that they just destroyed each other. A special example as well is if you have a wave on a string or anything that can hold tension. the velocity of this wave on a string is going to equal the square root of F times L over m, where F is the tension in the string. That'll be measured in newtons. That's just the force. Do not be confused with frequency, which is also denoted by F, but generally a lowercase f, measured in hertz. Not the same thing. L is the length of the string, and m is the mass of the string. So the length will be in meters, and the mass will be in kilograms, if you want to get a velocity in meters per second. Now, standing waves are where things get really, really, really interesting. If I continue to send a pulse of any wave type over and over and over and over again, it might bounce and reflect back once it gets from the far side. If the far side is closed, the pulse will come back on the opposite side of, basically a crest will turn into a trough on its way back. If it's an open end, it'll be a soft reflection, it'll come back on the same side. Either way, I get a whole bunch of interference with my own wave. So this works when you've got a wave contained in a certain space. Standing waves consist of nodes and antinodes. Basically, they produce what looks like a large overall wave pattern that doesn't have a forward velocity. And they consist of nodes and antinodes. The nodes are the spots where there appears to be really no motion of the medium. The antinodes are where you get the maximum motion. They head to what looks like a crest and what looks like a trough. And they oscillate back and forth between that. Again, at a fixed end, you get a node. So if both ends are fixed, you get a node on both sides. The first harmonic is only going to be taking you from one node to the next node. It's the simplest way to get from one end to the other with as little going on in the middle as possible. The second harmonic will be, got another node in the middle there. So it's the second least complicated way to get from a node to another node. You're just adding more and more and more wave fronts. For a standing wave that is open on both ends, you get an antinode at the open ends. So for the first harmonic, I'll start, let's say, at a crest. I'll go down to a trough, and that's just half a wavelength. Or I'll go from a trough up to a crest. Simplest way to get from antinode to antinode with there still being a standing wave there, with as little in the middle going on as possible. Second harmonic, basically you just add another step, slightly more complicated, not too bad, and as you go up in harmonics, you get more and more complicated. And of course, sometimes you come across things that are open at one end and closed at the other. You'll have a node on the closed end, you'll have an antinode on the open end. Now be sure, for all of these harmonics, you can mark the length of the tube or string or whatever it is, as well as how many wavelengths or the percentage of a wavelength that is fitting inside there. Be sure you can equate that amount of wavelength to the length of the tube or string and solve for the wavelength. A helpful trick that you can use, like I mentioned earlier in the video, from a midpoint to a wave up to a crest, it's always a quarter of a wavelength. That would be a node to an antinode. You will need to know the speed of sound in air is 331 plus 0.6 times the temperature in Celsius. Again, this only works in air. It's not going to be the sound wave traveling through anything else. Ooh, and we explored beat frequencies a little bit. This is a phenomenon that occurs when two frequencies are really close together, but they're not exactly the same. The closer they are together, the more in phase with each other they'll stay, so you'll get constructive interference, a loud sound, but then they'll slowly shift and get out of phase with each other. Then it'll slowly shift and get back in phase, slowly shift and get out of phase. When they're out of phase, you'll get destructive interference, basically no sound. When they're in phase, you will get constructive interference, you'll hear a sound, and it'll produce what's called a beat. It kind of sounds like wum, 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 wum. If you were ever a part of an orchestra or a band or anything else, and you start to hear that in your section, that means someone is just a little bit out of tune. The faster it happens, the faster they get in and out of phase with each other, wum, 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 the more out of tune they are. Now, if they differ by more than 15 hertz, it'll be hard for the human ear to make it out. You'll probably just hear it as two different frequencies. We also talked a lot about the Doppler effect. If a source is heading toward you, or you are heading toward a source, and you're a listener, you're going to hear a higher pitch than what is actually being emitted, because the wavefronts will arrive more often than if you're sitting still. If a source is heading away from you, or you're heading away from a source, you're going to hear a lower pitch. And you can determine the difference in the frequencies with the Doppler effect equation. The observer's frequency equals the speed of the wave minus the observer's velocity, all over the speed of the wave minus the source velocity. Now that entire fraction, multiply that by the source frequency, and you've got it. The most difficult part of the Doppler effect is trying to figure out whether the observer's velocity or the source velocity is positive or negative. Basically, just look at, I always draw myself a picture of it, and look at the way that the wavefront is heading when it hits the listener. That is defined as the positive direction. So if VO or VS is in the same direction, they will be a positive number. If not, they will be a negative number. In the event they're a negative number, don't forget with the Doppler equation, since you're subtracting VO or VS every time, if you subtract a negative number, it's basically just the same as adding that number.